Hi everyone, I'm Xin Zhang from Peking University. I'm very pleased to introduce our work, a unified and efficient coordinating framework for autonomous DBMS tuning. My presentation has three parts. As a refined system, a database has multiple configurable components, such as knobs, index, material weights, queries, and so on. The DBAs are responsible for setting a proper configuration for those components. However, it is a daunting task, requiring domain expertise and resources and time for trial and error. We will show you some cases. A database has hundreds of knobs, controlling its runtime behavior. Given a workload, how to set appropriate knob values is proven to be an NP-hard problem. And building suitable indexes can speed up query execution, but there are a large number of possible index configurations with unknown benefit. How to select index to build within a storage budget requires domain expertise. Similar with index, building materialized views can speed up query execution, but the decision is also difficult to make. Rewriting a circle query can achieve higher running performance, but given the large number of different sequences of rewriting rules, query rewrite is NP-hard. Luckily, automatic tuning can solve those problems by carefully designed algorithms. There are intensive interest in machine learning-based tuning engines. They interact with the database and learn the benefit of different settings by principled trial and errors. This is a non-exhaustive list of current machine learning-based engines. They can find promising configuration for different components. However, current engines only target on a single and specific component. Recall that the performance of a database relies on multiple configurable components. When adopting those tools, the DBAs often have more questions, like, can the single component tuning agent find the best global configuration? And since adopting a tuning agent still needs the time and resources of replaying the workloads for trial and error, the DBAs will wonder, given limited tuning time, which components should I spend more time to tune? We conduct some case studies to answer those questions. There are dependencies between database components. For example, the knob for optimizer will affect the effect of build index, and when determining the size of buffer, the build index and the materialized views should be considered. Please have a look at the figure. We observe that only applying the knob config 1 and the index config 3 leads to the global optimal. To this end, the answer of the first question is that tuning a single component is hard to find the global optimal. Tuning multiple components together would own more advantages compared with the standalone tuning. However, when tuning multiple components, the question of allocating tuning budget among components is hard to answer. This is because, given an unseen workload, the potential reward of tuning one component is unknown and non-stationary over time. For example, the figure shows the performance improvement of tuning 3 components. We observe that tuning index has more gain, but we cannot keep tuning index, since its tuning gain does not increase as more budget is spent. We conclude to pursue higher database performance, we need a unified framework that can coordinate existing tuning engines and to capture the dependencies between components and to allocate the tuning budget. To achieve those goals, we propose Unit 2. It is a unified coordinating framework which has 3 key designs. A high-level abstraction to support existing machine learning-based tuning engines, a message propagation protocol to make the engines communicate and coordinate with each other, a budget allocation strategy to wisely allocate budget to the promising tuning engines. Here presents the overview of Unit 2. On the top of the figure, there shows APIs provided by Unit 2, which can support different kinds of tuning engines. Below the APIs, there shows two modules of Unit 2, which execute iteratively. First, the tuning allocation module selects a promising tuning engines to execute for a sub-budget. On the figure, the knob engine is selected. Then the selected agent configures the database following a message propagation protocol. Finally, the tuning reward obtained is returned to update the budget allocation strategy. The workflow ends when the tuning budget is spent out. Before introducing the two modules, we first discuss the abstraction provided by Unit 2. It helps us to better understand the machine learning-based tuning engines. The engines share an iterative workflow following a trial and error manner to tune the database. They utilize a machine learning model to suggest a promising configuration and evaluate the suggested configurations. Based on the evaluation result, they update the model to improve the future decision-making. We categorize the tuning agent based on the adopted algorithms and how they evaluate the suggested configuration. There are three types: Bayesian optimization-based, reinforcement learning-based, and reinforcement learning estimator-based. To support the three types, we define the following three base classes and provide the corresponding interfaces as shown in the table. Using those interfaces, it is easy to integrate an engine for multi-component tuning. The developer just needs to inherit the corresponding base classes and override its functions. Then I will talk about the budget allocation module. We formulate the budget allocation as a multi-unbounded problem. Consider a set of tuning engines. At its decision output, Unit 2 selects an engine to execute for a predefined sub-budget and observe its tuning gain. The aim is to maximize the cumulative tuning gain. Since the reward of tuning each engine is unknown, we adopt Thompson sampling to balance the trade-off between exploitation and exploration. At the first step, Unit 2 constructs the posterior distribution of rewards for each engine based on the observations. At the second step, Unit 2 selects an engine based on the probability sampled from the distribution, instead of greatly selecting the agent with largest expected gain. Recall that the tuning gain of one component is varying a long time. We use a memory buffer to control the number of considered observations to dismiss all information. Next, I will talk about the message propagation protocol. Under the protocol, the select agent gets a message from other engines and configure the database according to the messages. If a better configuration is found, the engine updates the message for other engines. The first question is why we need to broadcast the message between engines. The machine learning model of existing engines operates under the assumption that the configuration of other components are fixed. However, when tuning multiple components, the machine learning model of component A will be inaccurate if the configuration of component B or others is changed. To solve this problem, we make the agents adapt to the environmental changes, which is the context. We explore two sub-questions: how to characterize the context and how to make the agents learn across the context. We adopt the internal metric of database to present the context and encapsulate the context feature in the models of tuning agents. Before tuning, the agents first gets the context feature, inputs to its model, and suggests a corresponding configuration. Now, I will talk about evaluation. We evaluate Unit 2 coordinating 3 agents on 3 workloads. We adopt total query execution time of the given workload as the performance metric. We compare Unit 2 with 3 types of baselines. The first is standalone tuning, which tunes a single component with a single agent, as previous studies did. The second is sequential tuning, a naive way to tune multiple components in a database. Given a tuning budget, a DBA allocates it equally to the tuning agents and grants them in turns. The third is UDO, which adopts a two-layer schema. In the outer layer, the index agent suggests and applies an index configuration. Then in the inner layer, agents for knob and queries iterate for a fixed number of iterations. The results show that Unit 2 finds the best configurations on all the 3 workloads along time, achieving up to 40.1 times speedups on the execution time compared with the baselines. We also conduct ablation study of context feature. We observe that adopting context has better performance. And we also compare different budget allocation strategies to showcase the advantage of Thompson sampling with a buffer design. Unit 2 executes agent alternatingly to tune multiple components in a database. Another solution is to adopt a central agent over the joint configuration space. We compare with such an approach. We tune the knob and index components. We observe the joint optimization proposed worse than the Unit 2's alternating one. This is because the joint optimization has a scalability issue due to the exponential growth of configuration space when drawing the subspaces. In a summary, tuning multiple components of a database is necessary for pursuing higher performance yet challenging. We propose a unified coordinating framework Unit 2. It contains a strategy to allocate the tuning budget among the agents and a coordination protocol to enable collaboration among tuning agents. We also define the interfaces for a broad class of tuning agents, which are simple for integration with existing approaches and for future extension. Thanks for listening.